Hello, my name is Hong Chan. I'm from SK Telecom, which is the largest telecommunication company in Korea. Today, I'm going to introduce our collaboration work with Intel, focusing on our network quality analysis and prediction use case. Our presentation is going to follow this order. First, I'm going to introduce a quick demo for network quality analysis visualization. Next, I will briefly cover network quality analysis in SK Telecom and our own in-memory data store for Apache Spark called FlashBase. Then I will explain how we accelerated deep learning preprocessing by using vectorization. From this part one, I'm going to hand it over to Jason, who is a senior principal engineer in Intel and Apache Spark PMC member and the creator of Intel Analytics 2. This demo will visualize network quality analysis regions at points with different colors on the map and dynamic charts on the right side. For the points, to the blue color, it means the better quality, and to the red color, it means the worst quality. If we move the location or choose the different time spans, graphs and charts are updated right away according to its location and time span ranges. The data set has 100 million records. Zooming out means querying more data to aggregate and visualize the points and charts. This instant update is possible because we accelerated query processing by using aggregation pushdown and vectorized processing. Okay, let's see the demo. Next, I will briefly introduce our use case and our in-memory data store for Apache Spark named FlashBase by summarizing last year's talk. As I told you earlier, SK Telecom is the largest telecommunication company in Korea. Our company has half the population of our country as our subscribers. To support them, we have 300,000 cell towers. And each cell tower, the network devices that connect our subscribers to our core network, generates a huge volume of logs in a very short time period, like 10 seconds. And each log has geospatial tags according to the cell tower's location. In 2016, we tried to build a real-time network quality analysis system which can ingest 1.4 million records per second, meaning 120 billion records every day. And at the same time, we need to return the network quality analysis result in a few seconds for specific time, for specific location. Looking back, it was challenging requirements which could not be solved with the big data technologies at that time. First, we tried to solve this problem based on hard file system and Apache Spark. But hard file system cannot efficiently handle numerous partitions with very small size data, reflecting specific locations and specific time. So we tried to build a new data store for Apache Spark named FlashBase, which can support much more partitions with much smaller data size than hard file system. So we gathered the best known open source software. First, Apache Spark for SQL interface and distributed query engine. Redis for DRAM key value store, and RocksDB for SSD key value store. And SSDs for shorter latency and small-side parallel IOs. I thought that we could easily build a new data store by just integrating them together. However, it has been very challenging to breathe life into a collection of open source softwares and make it as a working in-memory database system. But we have achieved it for the last 4 years. As a result, FlashBase has the following features, which are mostly required for commercial in-memory database systems such as recovery, replication, scale out, and so on. Especially for ingestion performance, FlashBase can ingest 500,000 records per second in a single node, and each ingestion operation is handled in an atomic way. Especially, our data store can store billions of partitions by taking advantage of key value store and in-memory storage devices. This can be used to greatly reduce the search space for big data queries with filter predicates of high cardinality columns like time spans and locations. This is a query example of network quality analysis for specific time and for specific location. By using extreme partitioning and pushdown filters, we could finally reduce the query time for 0.1 trillion records to 1 second. So far, I have introduced our own in-memory data store for Apache Spark. From now on, I'm going to introduce our deep learning use case. Since SK Telecom is a telecommunication company, we need to predict various network quality indicators for anomaly detection and real-time network infra management. We first tried to network quality prediction in 5 minutes by using well-known sequence-to-sequence model. But the model could not predict sudden peak changes very well. Therefore, we came up with new memory augmented model, which can learn from the periodic changes of past signal patterns by using its own memory. For the details of this model, you can refer to the last year's talk. This is the test result of our model. Unlike sequence-to-sequence model above, the below our memory augmented model can predict the sudden changes very well. In the legacy architecture of data pipeline for deep learning, we had inefficient bottleneck points from data source to deep learning inference, such as data exportation to disk files, serialization and deserialization with different data formats. To address this problem, we collaborated with Intel and implemented this new architecture of pure in-memory data pipeline based on FlashBase and Intel Analytics Zouwu. Through this pipeline, preprocessing and deep learning inference and training can be integrated into just one single Spark cluster. Furthermore, the whole pipeline is based on Apache Spark's RDD without any collect operation. After pre-processing job is done by FlashBase, the results are delivered to Intel Analytics Zouwu as Spark's RDD. And Analytics Zouwu performs inference operations with vectorized processing by exploiting Intel CPU's SIMD instruction set. Consequently, we could reduce the end-to-end inference time substantially, and more details will be covered by co-speaker Jason later in this talk. Okay, so far I've covered our deep learning use case. Now I'm going to explain how we accelerated deep learning pre-processing by using aggregation, pushdown, and vectorization. So what is pushdown? It means offloading computations to low-level computing modules, which is closer to the original data source. In other words, it means near data processing. Currently, Apache Spark can push down only filter predicates and projected columns to external data sources. If aggregation queries are executed, Spark push down filters and projected columns to the data source first, and then the only filtered data are retrieved to the Apache Spark's executors. Finally, Spark executors handles the aggregation operations. But what if aggregation can be done in the external data sources? As pushdown filters can substantially reduce the data size to be transferred. With aggregation pushdown, Spark executors can retrieve only pre-aggregated results, thereby greatly reducing the data size for data processing and data shuffling. Moreover, vectorized processing in the data source can utilize modern CPU's native SIMD SIMD instruction set, such as AVX, AVX2, and AVX512, which can process up to 16 floating point data in a single instruction at the same time. This is our design for aggregation pushdown. Because the original Apache Spark does not provide aggregation pushdown feature, we use Apache Spark's Catalyst optimization rules. We defined a custom optimization rule named propagate aggregation rule and appended it to the original set of rules. This custom rule is executed after finishing the original optimization rules in the Catalyst optimizer. This is an example query to retrieve count and average height of engineers grouped by years. The original plan is executed in the following order. First, relation plan builds RDD from the data source. Then the logical relation defines the attributes in the data source. Next, the data of RDD are refined by the filter plan, and the columns are selected by the project plan. Finally, the pruned filters data are aggregated by the aggregate plan. In order to push down aggregation operations, we created new relation class named relation for aggregation and replaced it with the original relation class. Then we made new logics for Apache Spark to be able to push down the expression trees of group by and aggregate functions to the new relation. This looks simple, but we face many problems to implement this idea. Because current Apache Spark is not designed to conveniently push down the aggregation operations. In more details, our custom rule transforms expression trees into attributes and wrap them inside the project plan. Finally, the new relation for aggregation gets the push-down expression trees for aggregation encapsulated by the attributes in the project plan. And the logical relation is also changed, reflecting the updated attributes in the project plan. And the box at the bottom right side of this slide shows the query explain results, which shows the final optimized logical plan customized by our new optimization rules. Inside our data source, FlashBase handles the push-down aggregation operations and the expression trees. FlashBase has a columnar data structure having similar data layout to Apache Arrow. So the computation operations can be easily vectorized. FlashBase makes groups, and for each group, aggregation operations are executed, accelerated by Intel CPU's SIMD instruction set. Okay, this is the test results. This is the training data set for the network quality prediction with 8 major index columns and 0.7 billion records. Using this data set, we conducted our experiments, and the test result is like this. For data normalization in deep learning, we need minimum and maximum average aggregation values for the entire data set. As you can see in this table, min-max average operations are accelerated by aggregation pushdown and vectorization, and the performance gain was up to 8 times. Next, in order to produce 5-minute time interval average values from the original log data with 10-second time interval, group by aggregation operations are required. Since the group by aggregation required to create a hash table inside the FlashBase data store, the performance gain was reduced, but it was still about 2 times faster than the original version. This is an initial result, and the performance keeps improving. And also, if we break down the performance gain for the data normalization test, current performance gain from vectorized processing with similar instruction set was about 1.5 times. The dominating factor for acceleration is from aggregation pushdown itself, which is 5 times, by reducing the data transfer size and later computations. Theoretically, current SIMD instruction set can enhance performance up to 2 to 3 times. We discovered that the smaller gain of our vectorized processing was from inefficiency in FlashBase scan operations. We are addressing this issue now, so we are expecting enhanced performance gain from vectorization soon. Okay, that's all for my presentation. From this part one, I'm going to hand it over to Jason. Thank you.
Thanks, Nate. So as mentioned by Nate, we have been working with SKT to enable the unified end-to-end big data analytics and AI pipelines for SKT's network quality prediction. So that the entire data analytics and the deep learning training and inference pipeline can run on the same Spark cluster, scale out transparently across a large cluster, and everything is done in memory. First, I talk about the unified software architecture we have building with SKT using Analytics Zoo. At Intel, we have been focusing on bringing AI or deep learning to big data. We have open source BigDL, which is a distributed deep learning framework for Apache Spark. With BigDL, people can write normal Spark code, just like they use MLlib or Spark SQL, but now they can use BigDL to write new distributed deep learning applications on Spark. In addition to BigDL, we have also open sourced a new project we call it Analytics Zoo, which is a high-level software platform building on top of those deep learning frameworks like TensorFlow, PyTorch, Keras, and as well as other big data distributed analytics frameworks like Apache Spark, Ray, Apache Flink. The goal is really bring all those deep learning technologies, whether it's TensorFlow or PyTorch, to a big data platform and run it in an integrated and distributed fashion. So this slide gives you a very quick overview of Analytics Zoo. As I mentioned before, it is built on top of all those deep learning frameworks like TensorFlow, PyTorch, also OpenVINO, and so on, and utilize Spark, Flink, Ray, etc. to build a distributed end-to-end data analytics and AI pipeline. Inside Analytics Zoo, there are 3 layers. At the bottom layer, there is a so-called integrated data analytics and AI pipeline, which is a horizontal layer that allows users to apply the AI or deep learning models like TensorFlow or PyTorch and so on Spark in a distributed fashion. On top of the pipeline layer, there is an automated ML workflow layer, which provides automated processing for many of the machine learning tasks. For instance, we have built a AutoML support for time series analysis. And at the top layer, there is also a set of built-in models, such as the recommendation models, time series models, and so on. People can directly use in the underlying workflow and the pipeline. Of course, one can also use any standard, say TensorFlow or PyTorch models, directly use it in Analytics Zoo as well. So Analytics Zoo is an open source project, and you can refer to the GitHub link on the slides. So let's look at some concrete examples on what we mean by applying deep learning or AI models to your Spark data pipeline in a distributed fashion. So this is one example. Actually, this is used in SKT's use case in that we allow the user to apply distributed TensorFlow models directly write your TensorFlow code in line with the Spark code, which can then run distributed across your Spark cluster. So as you can see, user can use any Spark code to process the data, maybe to get a RDD of data set or data frame, and then take that RDD or data frame. We provide an API, basically take your distributed data set across the cluster and then transform it into essentially an RDD of TensorFlow tensor, or in memory, or distributed across your cluster. And then you can use any standard TensorFlow code. In this case, we are using some Slim code to build a TensorFlow model. And after that, you can use the API provided by Analytics Zoo for distribution or inference. Under the hood, we essentially replicated the TensorFlow model distributed across the cluster. And then on each worker, we will feed the partition of the TensorFlow tensor we just prepared previously, and feed that data into a TensorFlow model. So we can compute a local gradient on each worker. And then we also provide a in-memory or reduced layer, which is built on top of the RDD block cache layer, the Spark block manager, to perform in-memory or reduce parameter synchronization across those workers. So essentially, we can transparently run the distributed training or inference with your standard TensorFlow model, and which use your Spark data processing, whether it's RDD or data frame as the input data. Another example is, for instance, a lot of the users are really, Spark users, they have built their pipelines using Spark data frame and Spark ML pipeline. And we allow those users to directly use deep learning models, for instance, Keras models in this example, inside your Spark ML pipeline. So let's look at the SKT's use case. As Nate mentioned, after you get all the data stored in your big data cluster in the Lightning DB, in SKT's case, and then you can process your data using Spark and Spark SQL. Previously, you will need to somehow export your data, maybe export it into a CSV file, and then pre-process it, and then copy it to a different GPU cluster. So you move the data across between those clusters, and then you process your data, maybe using pandas, maybe using Dask, and then run the training and the inference on those data. So essentially, you need to manage multiple frameworks, multiple separate clusters, and you have basically two separate workflows, which you need to use some glue code to tie them together. We then work with SKT essentially to transform that into essentially a unified and end-to-end architecture. So you can run the pre-processing using Spark SQL. Everything is in memory, and then you can get a set of RDD clusters. And after that, use Analytics Zoo to take the TensorFlow model and run the distributed training and inference on the RDD of TensorFlow tensors in memory. So as you can see, there is a lot of benefits of running a unified end-to-end architecture using Analytics Zoo. First of all, you reduce a lot of overhead in terms of data export, data copy, and so on. And then secondly, it makes the entire pipeline much more productive, because you're writing all the program and one Spark job or one Spark program, and it can run on your Spark cluster, and everything is automated. So let's look at some of the performance improvement by using analytic zoom compared to using a separate GPU cluster. On the left side, this is the comparison of the inference performance. As you can see, as we move from a separate GPU cluster to an integrated pipeline using analytic zoom, on a single node, we can get about 3x speed up in terms of the end-to-end inference pipeline. And then analytic zoom allows you transparently scale out your inference pipeline. Users do not need to change any code, but we leverage Spark to transparently run the inference pipeline on 3 nodes and give you additional speed up. On the right side is the comparison of the training performance. As you can see, using one server, one CPU server, and with the training performance is actually about the same as one GPU card. And then again, the benefits of analyzing, it allows you transparently scale out your training pipeline. Again, users do not need to change any code. It just can transparently scale out to a distributed fashion. And use 3 nodes in this case, we again get about more than 3x speed up. So we have been working with SKT on this end-to-end Spark analytics and deep learning, in particular distributed TensorFlow, in a integrated and unified pipeline using analytic zoom. So as a future work, we are looking for additional solutions try to improve the time series analysis on analytic zoom. Project Zouwu is a new project we just kicked off. It's an open source project built on top of analytic zoom. It provides a high-level application framework for users to easily develop their time series analysis applications. So as mentioned before, analytic zoom provides other integrated pipelines, ML workflow, as well as built-in models. On top of that, we have put together a set of time series use cases and built-in models for time series analysis, as well as a module called AutoTS, which essentially is a AutoML framework specifically for time series analysis. So it automatically generates features, select models, and tune hyperparameters for your time series analysis. So Project Zouwu is an open source project. You can check out the GitHub link on the right bottom. Essentially, it allows you to easily build your distributed time series analysis pipelines, including feature engineering as well as deep learning models with AutoML support. And in particular, we built a lot of use cases for common telco applications, network KPI forecasting, anomaly detection, and so on. And it's optimized and scalable using Spark running on top of a large cluster of Xeon servers. So it integrates also the library, the TensorFlow, PyTorch, MKL, MKLDNN, and the scale out, transparent scale out to the cluster. So yeah, that's a future work. I mean, some work in progress we're currently working on, and you're welcome to look into details on our website. Thanks. That's all for our presentation.